Okay, so today I hope to answer this question. What is an infinity operad? And the thing that I would like to remark immediately for people is that this is about a new model for the theory of non-symmetric infinity operads. So I'll define what this is in a second, but that's what we are after. And so by the end of today's lecture, I hope to say, okay, this is the answer, okay, to this question. So we already have an idea from Walker's lectures, for instance, or from the literature. This infinity stands for homotopy coherent structure. Okay, so what we really want is theory of homotopy coherent non-symmetric operads. Okay, so we'll build the combinatorial framework towards that. Okay, so we will build a combinatorial framework. Similar to simplicial sets for this purpose. And the other thing I want to preemptively say is that this is joint work. The paper is out recently with my former advisor, Özgün Ünlü. So the paper is called Simplicial Lists in Opera Theory 1. Okay, so let's get started, and first of all, forget this infinity and let's sort of review this notion of operad and what they are good for, etc., and what is it about before we go to the coherent case. So let's just write down the definition. Okay, so I'll put, so this will always be assumed non-symmetric and let me just put this here as well, colored operad P consists of the following data. Number one, we have a collection of colors, and this is just traditional terminology. You can think of these as like maybe objects in analogy with category theory. So we have some objects which we call colors. Why we call them colors? Classical literature. Okay, so say A, B, C, etc. Now, well, this is the first piece of data. The second piece of data is operations. Say, I don't know, FG, etc., which have. So you can think of these as sort of morphisms, okay? Except that we have the domain is a sequence of objects, and the codomain is an object. So which have a sequence of colors as source and the single color as target. So typically, an operation of the form, so we can have sort of f, and the domain is a sequence, which I will denote with underlined letters. So this is some sequence, A1, AK of colors, to the single color, say B. So this is what these operations look like. So this is depicted. So for monoidal categories people, which we all of us are now. So in string diagrammatic terms, or we say in the language of trees, as a corolla. So this is, say, so let me use, okay. So we have the operation, say this sort of node, and we think of it as having inputs A1 to AK and output B. So we read it top down. So yeah, this is a useful heuristic sort of to imagine what operations look like and to understand what follows. Or you can think of it as a generalized notion of morphism from a sequence to a single object to make analogy with category theory. So both are useful. Okay, so we have this data, and now we have a composition operation. Well, I should let me not use the word operation. So a composition, what? Operation, whatever. Composition operation, which I'm gonna depict first. So what are composable things in an operad? Well, so let's say you have an operation G, target is C, and you have like B1 up to BK as source. And then on top of these, if we have operations F1 up to Fk, and they have their own sort of sets of inputs here, we can compose them into a single operation. So let's denote these A11, etc. A1, whatever. I'm not indexing properly. So let's say, and this is sequence AK. Okay, so given, let's write this. So given G from sequence B to C, and given Fi's from sequence AI to BI, we can form the composite right? So what's the composite going to look like when we sort of squeeze the mid-level here is an operation G composed with sequence of F's, and what we get here is like we concatenate all of these. So we have sequence A1, let me write star for concatenation, sequence AK, and the output is this C. Okay, so we get a composite G composed F bar, or also written as G composed with F1 up to Fk, depending on what you want to emphasize. And this goes from, well, let me not specify it because I put it here. So from the concatenation of these top sequences to the bottom sequence. So this is how you compose. Okay. And moreover, I mean, this should be associative and unital. So we say for all colors A, we have an identity operation. Just write 1A, A to A, or sort of 1A, A to A. And all of this data is such that composition is associative and unital. Okay, so that's what an operad is. I haven't seen an infinite version, to be honest with you. It's possible, but yeah, I mean, there are ways to write this so that you could. So if you have a particular example in mind, we can discuss it, like, because it would be interesting. I mean, if you think there is an interesting example which is not covered by this, I'd love to hear it. Yeah, but this is the assumption. Yeah. Yeah. Okay, so we can sort of understand from this that what we have done is just generalize the notion of category to include sort of morphisms like this, from a sequence of objects to an object. And we have extended the composition scheme appropriately. Okay, so that's what an operad is. And so sometimes in the literature, for this specific type of object, you will see the term multi-category. Many people have preferred this term, although operad is like the dominating term. So we can call these A bar to B like multimorphisms. Yeah. And so that's one thing. So the reason I say colored is because historically, the first examples of operads have a single color, not a set of colors, not a collection of colors. And that's similar to categories with one objects, which are monoids. So these objects, yeah. So I think the first occurrence of this object in the literature due to May, there was one color and it was enriched in topological spaces, and and it was symmetric. So it's a kind of odd combination. But then as the literature expands, sort of we have this base sort of object of study. In Leinster's book, you will see, for instance, one of my favorite references, term multi-category being used. Right, so another thing I want to just say in words, why did I emphasize non-symmetric? And it's odd to emphasize something which is not there. So something is an operad is called symmetric if any permutation of the inputs gives you a new operation. And I'm not assuming that. for combinatorial reasons today. Okay, so our paper is devoted to non-symmetric operads. We hope to extend our approach to symmetric case, but for now, this is. And there are interesting examples of things which are non-symmetric. So, yeah. So let's get on with why this is useful and how. So let's put first. Yeah. The what? So little cubes operad is uncolored, and it's yes, there is a single color. So when you say uncolored, it means there is a single color. Yeah. It is symmetric and enriched in topological spaces. We'll come to that. Yeah, I will not come to that. I will not discuss the example, but yes. So those are the classical first operads in topology for loop spaces. Yeah. Yeah. So I'm interested in this angle of doing analogy with category theory. So let me just put down the first example. So any category is an example of an operad with unary operations only. So what I mean by unary is that we have a single input and a single output all the time. So you can make any category into an operad. In fact, we have an adjunction So I don't remember which one is left or right, but let me just write it down. So we have categories and we have operads. And we have this inclusion here, which sees every category as an operad where every operation has a single input, right? That's what we are generalizing actually. And so this is inclusion. Let me write it like that. And this we have a functor here, which I'll denote this. So you can take any operad, discard all the operations which have multiple inputs, keep only the ones with one input, and you get a category. So P1 is the category of unary operations. And this is right adjoint. So right adjoint. So this is one of the connections between categories and operads. I guess I should say what a morphism between operads is very quickly. So definition. So a morphism of operads, I'll just say is a structure preserving map. So you can have like a phi from operad P to operad Q. And as you can imagine, it maps colors to colors, operations to operations, preserves number of inputs, preserves identities, preserves composition. That the first thing you imagine. Okay, so that's the notion of morphism in this category here of operads. Good. Okay. Yeah. This one. So you take any category. This one. Yeah, you have an operad, and you just discard everything which has multiple inputs, right? If you think about it in terms of these multimorphisms, yeah, you forget about all morphisms with multiple inputs. Keep only the ones with one input, and then what you get is a category because you have morphisms, right? So you forget part of the structure, you get a category, and it's sort of a forgetful functor which is right adjoint. Yeah. No? You seem like you want to say something.
Oh, it's also worth pointing out that it's a full subset.
Yeah, okay.
Like, a category is just the same thing.
Yeah. So, yeah, this is to point out that operads really generalize categories. Okay. So, unfortunately, now I'm going to have to erase. But I hope the intuition is clear. Like, just morphisms from many inputs to an output and composition. Oops, pictures first. Okay. And so now let's get into the more interesting examples. Although that's interesting. Yeah. The what? The underlined where? No, this is not an underlined C. This is subset.
Oh, I see. Okay. But again, so category is regarded as an operand. How? Because you need n inputs, right?
So every category, I mean, in a category, what do you have? You have morphisms A to B.
Yeah.
So you consider them as operations from the singleton sequence A
Oh,
to
the rest is empty. Okay.
yeah, like you can consider morphisms in a category with one input and one output.
Okay, I thought you
Yeah.
would say you have to choose an operation. Take the answer, then it's okay.
Yeah. So yeah. Okay, so I would say one of the main examples, or the main example we have, is this. So if you have a monoidal category, V, so this is monoidal product, monoidal unit, so monoidal category. So there is an operad which we denote V tensor with so colors, objects of the category V, and operations and let me just depict them. So what is an operation? So now the colors are objects of V. Say A1 to AK, we have a sequence of colors to B. This is a morphism from the monoidal product of A1 to AK to B. So this is just taking objects of V, interpreting morphisms from the tensor of n objects, or K rather, as this type of operation. And I should remark here that so if we have like so we can have operations with no inputs, say F, and these are just morphisms from the monoidal unit to B. So this is how we interpret. So we can translate basically the monoidal structure into an operad structure. Okay. And yeah, this is important. So I mean, if we follow again from our other seminar, so if you follow this string diagrammatic intuition, say, how would you interpret this, right? We have the parallel A1 to AK, we tensor them, and you map into B, that's it. Okay. Okay. So this is the example. So we have a functor which does this to monoidal categories. So from monoidal categories to operads. Okay. So every monoidal functor gives us morphisms of operads. And now this functor is right adjoint. And just a little later, I will. So there is a right adjoint here, and it's a very important functor called monoidal envelope. Yeah. Yeah, there's a. Okay, yeah. This is left adjoint. Yes. Yes. Thanks. So I'd like to explain what this is in a minute. So let's do the natural progression of ideas here. So so the functor which, so you take this and you create this operad. This is functorial. And okay, there is a sense in which this is a forgetful functor, but it's a fairly long story. And this has a left adjoint, which is like a free functor from operads to monoidal categories. Yeah, yeah. So yeah, this is important for us today, so I'll explain it. But I'd like to cover some other things in between. Okay, so a morphism of operads like that. So phi p to q may be, or rather, I should say is, also regarded as a P algebra in Q. So there is this just change of terminology really, but this notion of algebra is important. So the best other case I know where this happens, so morphism of commutative rings, for instance, are sometimes called just algebras by algebraists. So morphism of operads regarded as algebra. So let me just say this. So typically, this shift of terminology, so especially if the recipient of the algebra is of the form V tensor, so we have a monoidal category. In this case, we would say P algebra in the monoidal category V. Okay. Yeah, and this is really the fundamental notion in operad theory, studying these algebras. And so that's why I wanted to carry out this definition. Now, from this example, so in particular, we have an operad set with the Cartesian product. And so what are the operations in this operad? Just morphisms from products of sets to another set. That's it. Yeah. So, and this, in classical operad theory, algebras are typically valued here, although that's not always the case of interest. Okay. Right. So let's just, I'll give a couple of examples just to motivate the theory, but this is not a lecture about operad theory where we go into very detail, just to say, so, so the terminal, yes, so, right. So usually Q is some sort of monoidal. So it could be abelian groups. You want to study algebras in abelian groups, algebras in topological spaces. And the most basic case is where it is just set. And in some sense, an algebra is some sort of Koper-Sheaf, like a functor into sets from a category would be an example of an algebra. So this is how we view these things. And so operads are useful because of the algebras they encode. Okay, this is how the theory came to be. So the terminal operad, so this is an important example. This is called the associative operad. So this is associative operad. And let me just quickly unpack what this is. Now, of course, being terminal, we have a single color, and we have a single operation with k inputs. So this is just now, in this operad, there is a unique operation where these are k many here. We have one color, so it doesn't matter what we call this, and one output. So let's call this something like whatever, like mk. Yeah, and this is for all k bigger or equal than 0. So this is the terminal operad. Now, the algebras so let's see, for example, in set, well, how do I form this? The morphism of operads from ASOC to, say, this operad of sets, right? So for the single color, we have to pick a set. So a color in sets is a set, okay? So this single dummy color, whatever it is, gives us a set. Let's call it A. And these operations with k many inputs will pick some operation A multiplied k times to itself, right? So let's call this what? Mu k or something. And if you follow up what composition does, etc., this will give A the structure of a monoid. So this is the k-fold multiplication. Okay? And how do we pick the monoidal unit? Well, if k is equal to 0, we have this operation, m0, and according to the prescription there, we interpret this as a map from the monoidal unit, which is just the single element set. So this is k-fold multiplication, and this is unit. And saying that this is a morphism of operads is the same thing as saying A is a monoid. So ASOC algebras in set are monoids. Okay, so the terminal operad records the notion of monoid actually. And so if we replace set by any category, really, or any monoidal category of this form, you get monoids in this monoidal category or monoids in a certain category, like in spaces, say. So monoids in, I don't know, abelian groups or rings and things like that. So we get all sorts of interesting examples. And what we are really after with this type of stuff is, so we want to capture some homotopy coherent stuff. All right, so the question that arises, and we hope to answer this question, maybe not today, but in the next lecture. So how do we encode homotopy coherent algebra, say, in spaces? So this doesn't have to be the case, but we want stuff like this. So in the particular case of spaces, these would be the classical notion of infinity space, right? So so yeah. Sorry, what?
By what you mean ASOC algebras?
Yes. So homotopy coherent ASOC algebras are supposed to give us a notion of A infinity space. So we want notion of algebra which sort of doesn't strictly commute and which gives us up to homotopy sort of things. Right? So imagine, for instance, we have homotopy associativity of this multiplication. Okay? And that's one thing we would want to encode. In general, we want to do this for any operad, right? Talk about homotopy coherent algebras and things like that. So this is where a good theory of infinity operads comes into play. It does this. It's supposed to do that. Okay. Yeah, I mean, we get a model in our paper for infinity space. Oh, I mean, you explain what this is in. Okay, so think about it. So it is. So let's say we have some infinity space. So X, say some space. It has the structure of a monoid, which means that you can always multiply, say, X times Y times Z, right? So we have these k-fold multiplications for each k, but the associativity is up to homotopy. It's not, I mean, up to coherent homotopy, I should say. So for instance, if you say, if you have these, so these three in a monoid are equal, but in an A infinity space, these are just homotopic things.
The canonical example is the loop space, pointed topological space.
Yeah.
Generalization of the H space.
I think by H spaces people mean monoid in the homotopy category. So that would be covered by just operad theory. You take the homotopy category of spaces, look at monoids there, you get an H space. A infinity is you have homotopies and layers of homotopies, like everything is coherent. So it has a monoid structure, but everything happens homotopically. Let's say. If you want to comment, feel free. Yeah.
In the case of an associative H space, also the multiplication is not strict.
So it's not strict, but you are not saying anything about the homotopy who witnesses that.
This is a generalization.
No, no, no.
No, it's actually, this is a stricter condition. So, like, if you take what he's doing one level up, so it's not a generalization, there's a smaller class. Not every monoid in the homotopy category will necessarily have a lift to something coherent.
So this is the useful notion. Right? So the idea of monoid in the homotopy category, yes, it's good, but this is what turns out it's really useful. So where you choose coherence information in all levels of the homotopical structure, that's what you really want. And so, I mean, this is just to motivate this idea. And so this is a classical object of study in algebraic topology. Nowadays, people are interested in general algebras of any operad which behave in this homotopy coherent manner. So we are after that type of idea. Okay? We want to model what homotopy coherence is. How are we on time? So I have like a half an hour. Good. Okay.
I have a question.
Yeah.
Is it possible to do threshold algebras with some sort of homotopy spaces?
Azok algebras in the homotopy category of spaces, are they the same?
No, I
as-
thought
no.
go from any spaces to that, no?
You can get associative algebras out of
Yeah.
spaces like
Oh,
right, because then homotopy becomes
Yeah.
equality, or any functor that collapses homotopy equalities, any homotopy variant.
that's what I thought, but then
Yeah.
it's not in the way where we get like some homotopy.
No, you cannot go from here to here. Like,
Line, right?
yeah, from this to this, yeah, you can.
Okay.
Yeah.
Like pi octaves.
Yeah.
Yeah. So this is really, I mean, again, just classical example I'm throwing out here as motivation. So these Stashev has his classical papers here. There is Bortman-Vogt after that, and like subsequent development of the theory, and it's all like good. And recently, given the development of infinity category theory, the way we have been talking about it, there is again interest in this type of stuff again. So yeah, I'd like to move in that direction and sort of explore this. I mean, this is just an example. Okay. Right. Yeah. Yeah.
You're trying to, because you cannot define by putting the infinite space on the right hand side, you're trying to change the operator theory so that you can define.
Yes, exactly. So this is the sort of, these are a generalization of a category. So in an operad, you have sort of strict composition and things like that. An algebra respects the strict composition and gives you some interesting structure you care about, like monoids, for instance. And now we want to have homotopy coherent version of this theory. We want to say, oh, we have these operads where composition happens up to coherent homotopy, like they do in quasi-categories, for instance. And by creating algebras, oh, we have these homotopy coherent stuff as algebras. And we want a good theory of these things. So an infinity operad is supposed to encode this type of idea. So, yeah. Any other? Okay, so what we have seen is like for categories, so we have categories, and we have simplicial sets, and we have our nerve construction, and now infinity categories can be modeled as quasi-categories. Okay, so here we say infinity category is certain simplicial set, which are quasi-categories, right? Now, what I want to do and what we started sort of our first sort of attempts with Özgün, how can we have this combinatorial framework or something like this for operads? So they question, what do we put here? Can we have some sort of nerve and things like how can I combinatorially keep track of what an operad is, basically? And is there a simplicial way to do that? Because that would be so nice. And the answer is yes. Okay. So we developed this idea, which I'd like to briefly talk about today. And I guess in the next lecture,
The answer is not just a sequence of morphisms.
sorry, a sequence of
Nerve construction.
so the nerve construction is yeah, let's see, right? So how do we do? So the thought process behind our construction is the following. So in a category, so say C is a category. Now, how do you record in the nerve a morphism, say, from A to B, right? So you would say F is an element of, is a one simplex, and D1F is A, which is the source, and D0F is B. So this is how you record your nerve. And then higher simplices use composition, etc. Now, if I have an operad P, my morphisms are of the form A bar to B. So if I want to say that whatever, say I want to construct some nerve, I would like this, right? Like each operation is a one simplex somehow. How do I do that? Because, okay, fine, I can say that D0F is just B, good. But now I need D1F is this whole sequence of things. But D1 is supposed, I mean, if we go with the simplicial idea, you go from one simplices to zero simplices, right? So I'm supposed to take F now to the source. So I need a notion of mapping, which is not a function. A function would assign a single color, right? And so the idea is that we need a notion of mapping between sets which is not a function. I realize this is bad English, but Turkish English, that's what it is. So, perfectly fine English? Thanks. Okay. Yeah. Okay. So this is the initial sort of trigger, and then we get to think, okay, let's record this, etc. Let's see where it takes us. But actually, this was so in private, I'm sort of maniacal about writing definitions properly. And I wanted to write a definition of an operad in a certain way. I realized I couldn't. I got nervous about it. And then this. uh, then I went to Özgün and he said, yeah, okay. And we started developing the idea. Okay, so this brings us to a very sort of simple idea. Given that we cannot do this with functions, let's change the notion of morphisms so that this is valid. Okay, very simple idea. So let's do a definition. So I will define a category of sets now, which is appropriate for this. So let X be a set. So by Lx, I will denote the free monoid on X, which is just this joint union of the Xn, and this can be thought about as the set of sequences, so finite sequences in X. And so we define this important notion, which we call listing. A listing U from A to X, so A is another set. Maybe I should say A and X be sets, is a function A to Lx. So this is a Kleisli map. Right? So I'm doing the free monad on sets, and I'm doing the Kleisli category. That's what I'm doing. But explicitly, you can write it down like. So what does this do? It assigns to each element here a sequence here. It's just this type of mapping. So we can visualize it as sort of, yeah, I mean, you have an element. So this is, say, A and X. So the way I like to think about it is that there are, so it's like a multi-valued sort of mapping, say x1, x2, x3. It's like a multi-valued function, if you want to think. Multifunction would also be a good term. We thought about it, but then we dropped it, so we call it listing. Okay. And so, sorry? Yeah. So you could have things like this. And there is also an ordering of these, but the main idea is like a multi-valued sort of thing. Okay. And so we define composition. I will just say by concatenation and just briefly explain what I mean. So say we have A, which goes to x1, x2. These go to a sequence of things. This goes to a sequence of things. When you compose, you just do a composite. Like, so you take A to the concatenation according to the order here. Okay. So, and this is from the monadic perspective composition in the Kleisli category, to be rigorous about it. And so what we obtain is a category which we call list. Yeah.
If you're going to use this to define simplex category, you have too many morphisms. You want to do you need the image to be
That's yes, we have to. So yeah, I'll explain that, I hope, today. Okay. So actually I can do it right now. So we are interested, so for the special case of operads, because I mean, okay, this talk is about operads, but in the literature there are things like properads, props, all sorts of stuff, dioperads and things like that, with multiple inputs, multiple outputs, etc., which we would like to cover. But for specifically for operads, so we have the following object of interest. Okay, so let me not put things in definition form anyway. So we are interested, so a simplicial list our main object of study is a functor. Say x is simplicial list delta op to here. Okay, and I will say let's see here, so a morphism of simplicial lists say f between x and y. Now for simplicial sets, we say it's a natural transformation. Not really what I want here. Okay, so what we want these morphisms to do is to have functions as components, not these multi-valued things. Okay, so I will say is a natural transformation of two such functors such that for all objects of delta, the listing, so normally in a natural transformations, these are allowed to be listings, but I want them to be functions. So are functions. Okay, and and then to address the good point Özgün made, we are not interested for purposes of operator theory in all simplicial lists, but in a certain subcategory called operatic simplicial list. So here I will write definition. So a simplicial list is called operatic if for all morphisms in delta, say k to n, such that theta of k, so the last vertex here goes to last vertex here, we have that the induced morphism from xn to xk is a function. So it's perhaps not clear from this formulation how this directly impacts operator theory, but let's just do a little. So for example, So if X, again, operatic, so let's say, so this implies, for instance, the following. So let's say I have F like a one simplex. Okay. Now, first of all, the D0F, so D0 from x1 to x0 has to be a function because it falls in this type of stuff, right? I mean, the zero phase takes 0 to 1, right? So this has to be a function, which means that when I assign, so I will have like a singleton sequence D0F, which means if we think of F as some sort of morphism or operation, it has a single output, right? And D1 is a listing. So it will take F and assign a sequence of elements in X0 to it. So really, every one simplex in a simplicial list like this can be imagined as an operation. So this sequence is D1. And the output sequence is, so this is one little instance of how this sort of notion of operatic is adapted to describe operads. So how are we on time?
15 minutes.
15 minutes. Good. Okay, so now we have the sort of ingredients. So let me just say one more thing about this. So useful remark. So this is equivalent to saying that all faces and degeneracies are functions except possibly the last phase maps dn from xn to xn minus 1. So everything except last phase is a function. Which means, for instance, interfaces which record composition are functions. I mean, they assign a composite to things. Degeneracies which assign identities usually are functions. So we have well-defined identities, etc. Everything except these last phase maps. Because we need them to record, for instance, for one simplices, source of inputs and output.
When you have this sequence, how does the so you have A, x1, x2, and then other things on the right?
Okay.
Composition. You have D0, D1, D2. I can see it there, right, on this picture. These are the two simplex in your.
I mean, no, I haven't drawn a two simplex. I mean, this is just to explain how composition works.
Yeah,
for
I know, but I would expect functions, not functions except, but I would expect lists except. That's what I would expect.
you would sorry, what?
All phases are and degeneracies are functions.
Except last.
One of them is not.
Right? Yeah.
That's a list. I would expect the other way around. But I don't know the simplicity. So that's why I was.
Yeah. So no, that okay. So when we go to the simplicity, I mean, from here, right? I mean, if we decide that one simplices are operations,
One simplicities are fine.
yeah, then you want D0 to be a list and D1 to be a single thing.
Both statements are true.
Yeah. Yeah. Okay. So. I will briefly make some statements, perhaps comment on them next time, because I promised to say what an infinity operad is, so I'd like to do that. Okay, so right. So the idea is the following. So I have an operad P, and I have so zero simplices. So now I want to construct what we call listener of P from delta op to list. Okay, we can start the construction now. Okay, so NLP0 is colors of P, and just like for categories, so NLP1 is operations P. And so what should the higher simplices be? So say NLP2 is what? Well, if we follow the categorical idea, these should be sequences of composable operations, right? That's what higher simplices are supposed to record. And the general idea is that, so n simplices are leveled trees of operations well, with n levels. So let me briefly say what it is. So for instance, for a 2 simplex, what do I mean by level tree? I mean, well, is a tree with levels. So you have, say, something of this form and this. So you have like F1, F2. I'm not labeling colors. We have some colors here, whatever they are. Okay. So this, for instance, this configuration of operations in an operad would be recorded as an element as a 2 simplex. And how does the leveling work? The idea is actually quite simple. So and 2. It is quite simple. I mean, how would we depict the categorical 2 simplex? 0, 1, 2, something like this. Okay. So now these are leveled according to the categorical simplex, so to speak. Okay. So we have these trees and we have these levels of operations in each. And these are what our simplices will be. Okay. So formally, how much time do I have? 9 minutes. Okay, good. Yeah. That would be really, I mean, just in time, just the time to make some statements.
You have a second talk though, right?
Yeah, but I wanted to answer the question.
Okay.
Just to, yeah, I will not do any commentary, just write some stuff, and next time I can do more explanation. Okay, so but the problem is now, if I just say level trees, it's sort of not really well defined, although there are many ways to say what it is. And the way we record them is the following. So consider delta plus, this is the, it's like, let me say it like this. So it's like delta plus, we have an empty ordinal as initial object. So we take its nerve and say n simplices, take an element here, so call alpha. And these will be sort of just a sequence of ordered sets and functions, something like this. And now, so the point is that if I have a sequence like this, it encodes this type of shape. So let's just do this as an example of what I've drawn here. So if these colors were A1, A2, A3, B1, B2, and C, so how do I get, so what do I get is the following. So I have A1, A2, A3, to B1, B2, to C, right? So I can, so the shape of the tree is sort of recorded by these functions, and of course, this maps A1 to B1 and A2, A3 to B2, and both of these go to C because there's a unique thing. Okay. Right, so the idea is that given such sequences of ordered sets and sequence of functions, I can sort of recollect this tree from it. And then I can use this tree and map it into P to record simplices. And that's how we go about it. So very briefly, let me say here that this AN is, we want trees to have like a root. So this is just the one element set. Right. Now, the way we go about this is that, so first define multigraphs. And we define them as just, so we truncate the category delta to have just 0 and 1. And we do, we go to list. And we require this to be operatic. Right. And then we have, I can explain next time in more detail, but we have these multigraphs and operads. So we have this free forgetful adjunction here. And then for each n simplex in delta plus, so for this type of alpha, we record a multigraph we call M alpha. We apply the free operad functor. The alpha. And so then this, next time I can draw more pictures, etc., because this is very intuitive. But just to be able to make a statement and next time commentary on it. So basically I define list nerve of P and simplices to be, you take nerve delta plus something called rooted, which means this condition, whatever. And then I hit my operad with these trees of operations, and you define n simplices like this. So very simple, right? Like
That was so quick.
yeah, it's quick, but there's a picture, right? So a two simplex is just a two-level tree of operations. That's it. And you can even imagine how we do phases and degeneracy. I'll comment more next time, okay? Yeah, exactly. So this is, yeah, okay, good. So that's why you need the last phase. Yeah, exactly. So that's excellent. So that's why we need this. Because when I do D2, what D2 is supposed to do, you delete this, right? And what you're left with is a sequence of things. That's it. And if you think about it from this perspective, what dn does is sort of deletes this. But then what you're left with is like a sequence of things, and you can split everything. So you do get something operatic like that when you do this nerve construction.
So is it still the normally the composable operation?
Yes. Yes. So these are composable trees, level trees of operations.
When you first started talking about this, I thought you're going to change the simplex category.
That, okay, so next time we do that as well. So it turns out that simplicial lists have a pre-sheaf structure. So that perspective is also valid. Yeah. So yeah, I haven't talked. So I just wanted to, I mean, at least pictorially, it's clear why we are doing that. And as Ergen pointed out, what happens when you cut the root, you get a sequence. Right, so we have this combinatorial construction, and I will just state a theorem. The last two sentences I write. So this is a nerve theorem. So nerve theorem. So let X be a simplicial list. Then we have X isomorphic to the nerve of some operad. If and only if X is operatic, right? The condition of being operatic means it sort of looks like an operad, right? Shape-wise. And Lx is a category. So let me briefly, what is this? So Lx is basically the simplicial set whose n simplices are sequences of n simplices in X. You get a simplicial set this way. So why do you get a simplicial set? Like, just think about it intuitively. Now I'm doing sequences in X. I mean, the listings which assign sequences turn into functions because it's all sequences. Like that. But there is a theorem like this. I can expand on it next time because it's worth going into. So Lx, okay, so Lx, this is a simplicial set. So it's the simplicial set whose n simplices are sequences of n simplices of X. Yes. And now that's our objective. So I will say that X is a quasi-operad if this is a quasi-category. Okay, so this is my answer. So an infinity operad, I mean, I want to call it quasi-operad because it's that combinatorial flavor, right? But I do claim that this model's infinity operads is a simplicial list which is operatic such that this simplicial set is a quasi-category. So I hope I can say more stuff and explain some of the intuitions next time and some of the other theorems we have. So thank you very much for listening.